Section 1 Introduction. In the world of artificial intelligence and language models, we often talk about alignment. This is the process of making sure that the actions of AI systems match the intentions of their creators and the expectations of their users. When we compare this to supervised fine-tuning, SFT, in learning to generate, reinforcement learning from human feedback, RLHF, requires learning to discriminate first, which is simpler and more adaptable. RLHF involves two main steps. First, we use preference data gathered from a large number of crowdsource workers to train a reward model. Then, we use reinforcement learning methods to optimize the language model to maximize the reward. The reward model is a key part of the RLHF process, and our aim is to make it a reliable stand-in for human preferences. However, many researchers have highlighted the limitations of reward models and the challenges in using them to accurately represent human preferences. Currently, we need to address two urgent issues. 1. The dataset may contain incorrect and ambiguous preferences due to low agreement among annotators during preference labeling, about 0.6 to 0.7. Since we believe that human choice behavior is a noisy representation of underlying truths, it's crucial to detect and reduce noisy data to align learned rewards with true human preferences. 2. The reward model's ability to generalize is poor. If a reward model is trained on data with a specific distribution, it may perform poorly when it encounters examples that are out of distribution, OOD. This limitation may not only cause instability in the reinforcement learning process but also require the annotation of new preference data for online iterative RLHF processes. To tackle noise and ambiguity in preference data, we propose a preference strength measurement metric based on a multi-reward model voting approach. With this proposed metric, we can differentiate between incorrect, ambiguous, and normal preferences within the original dataset. Then, we can correct the labels of wrong preferences and smooth the labels of ambiguous preferences to prevent the model from overfitting on these low-quality data. In the loss function for preference modeling, we also introduce an adaptive margin based on the preference strength, making it easier to distinguish between similar responses. Our experimental results confirm that using reward models trained through the above heuristic methods can lead to a more stable reinforcement learning process and significantly improve the final alignment performance. To enhance the generalization ability of the reward model, we explore contrastive learning and meta-learning. By introducing unsupervised contrastive loss during the reward modeling process, the reward model can better distinguish subtle preference differences among responses. To bridge the gap between the preference data distribution and the model output distribution, we employ meta-learning to ensure that the reward model not only performs well on the preference data but also can distinguish the differences in target domain outputs. In this way, we make the reward model trained only on specific distribution preference data that can be transferred to OOD data. In addition, we can use the proposed method to continuously train new reward models to adapt to the output distribution of the newly aligned model, achieving iterative RLHF. On Anthropic's hydrogen hydride RLHF and OpenAI's summarization datasets, we can achieve consistent improvement of the language model in 3 to 4 rounds. The reward model infers human values and intent from preference data, so preference data needs to accurately and comprehensively represent human intent. However, in practical applications, preference data has some drawbacks. Firstly, preference datasets contain incorrect and ambiguous preferences. For example, in the annotations of preference data, there is a poor average agreement, about 63%, between Anthropic researchers and their crowd workers, and OpenAI found that the inter-annotator agreement rates among training labelers are at 72.6 plus or minus 1.5%. Secondly, different data contain preferences of varying strength. The responses in preference data are sampled from the SFT model, and most of the data exhibit low preference strength. The main focus of this section is to deal with the impact of incorrect or ambiguous data and make full use of data with different preference strengths. We review the RLHF pipeline, which has been applied to tasks like dialogue, instruction following, and summarization. This pipeline typically includes 3 phases: supervised fine-tuning, SFT, preference sampling and reward model, training, and RL fine-tuning using proximal policy optimization, PPO. The process usually starts with a generic pre-trained language model, which undergoes supervised learning on a high-quality dataset for specific downstream tasks, resulting in a model denoted as text, SFT. In this study, we focus on improving the remaining 2 stages. In the second stage, the SFT model is prompted with a user query to produce 2 distinct outputs. Human labelers are instructed to choose their preferred output, resulting in a chosen and a rejected output. By following the Bradley-Terry model, we formulate a preference distribution by employing the reward function. This function is used to calculate the probability of the chosen output being preferred over the rejected one. Treating the problem as a binary classification task yields the negative log likelihood loss function. In the realm of LMs, the network is often initialized using the SFT model. It then incorporates an additional linear layer on the final transformer layer to generate a singular scalar prediction representing the reward value. Section Summary. In this section, the concept of alignment in artificial intelligence and language models is introduced, which refers to ensuring that AI systems behave according to the intentions of their designers and the expectations of users. Reinforcement learning from human feedback, RLHF, is discussed as a method for aligning language models with human preferences, but it faces challenges such as noisy and ambiguous preference data and poor generalization ability. To address these issues, the authors propose a preference strength measurement metric and heuristic methods for training reward models, as well as techniques like contrastive learning and meta-learning to enhance generalization. Experimental results show improved alignment performance. Section RL fine-tuning. In the reinforcement learning (RL) phase, we use the reward function we've learned to give feedback to the language model. In simpler terms, we tweak the policy model to maximize a reward objective. This objective is a combination of the reward from the reward function and a penalty term that depends on the difference between the RL policy model and the initial model. This penalty term serves two main purposes. It helps maintain diversity in the generated responses and ensures that the RL policy's output doesn't stray too far from the initial model. Next, we aim to improve the reward model's generalization using contrastive learning and meta-learning. In reward modeling, a common challenge is that the model often fails to distinguish between chosen and rejected responses. This lack of discrimination can lead to poor performance. Contrastive learning, however, can help overcome this issue. It trains the model by comparing similar and dissimilar samples, helping the model to learn unique features within the data and enabling it to handle new, unseen data more effectively. When integrating contrastive learning into RL, we need to carefully choose the contrastive samples. We can either use pairs of responses from preference data or try to capture preference differences directly. We use two methods for contrastive learning: SWAV and SIMCSE. SWAV is an unsupervised learning approach that clusters data while ensuring consistency between different views of the same instance. It involves creating multiple views of an instance, predicting the cluster assignment for each view, and then swapping the cluster assignments between views. This method allows for more efficient learning and avoids the need for comparing every possible pair of images, which can be computationally expensive. SIMCSE, on the other hand, is a simpler method for learning sentence embeddings using contrastive learning. It involves using identical sentences as positive pairs, which are fed into a model to obtain embeddings. These identical sentences are passed through the model under different dropout masks, creating variations in their embeddings. Negative pairs are formed from different sentences. This approach allows for efficient and effective learning of sentence representations without the need for complex data augmentation or externally labeled data. The total loss of the reward model is a combination of the original loss and the contrastive learning loss. The original loss is computed using all original samples and their augmentations, while the contrastive learning loss uses methods like SWAV or SIMCSE to enhance the model's ability to recognize subtle variations and similarities in the data. A hyperparameter is introduced to adjust the impact of the contrastive learning loss on the overall reward model loss. Our results show that the methods based on contrastive learning are more stable in terms of training set reward and returns, ensuring a consistently stable RL process. We also found that the language model trained with the reward model based on contrastive learning performs slightly better, with the best overall performance achieved by directly incorporating SIMCSE into the reward modeling phase. Section Summary. In the RL fine-tuning stage, the reward function is used to provide feedback to the language model, optimizing the policy model to maximize the reward objective. The KL divergence term in the reward objective serves two purposes: preserving generation diversity and preventing mode collapse, and ensuring that the RL policy's output aligns with the accurate reward model distribution. In the context of preference generalization and iterated RLHF, contrastive learning is employed to improve the generalization of the reward model by effectively learning unique features within the data and exhibiting better generalization capabilities. Two approaches for choosing contrastive samples are preference pairs and preference difference. SWAV and SIM-CSE are methods used for contrastive learning, with SWAV involving clustering data and enforcing consistency between cluster assignments, and SIM-CSE using identical sentences as positive pairs and different sentences as negative pairs to learn sentence embeddings. The total reward model loss combines the original loss and the contrastive learning loss, with the hyperparameter beta adjusting the impact of the contrastive learning loss on the overall optimization. Contrastive learning methods show more stable training and better performance in evaluation compared to the baseline and SFT methods. Section 3.2 Meta-RM. Aligning with shifted distributions via meta-learning. In this section, we'll discuss our method, Meta-RM, which is designed to keep the reward model effective even when the policy model's distribution changes during PPO training. The main idea behind Meta-RM is to train the reward model in such a way that it minimizes the loss on the original preference pairs while maximizing the differentiation between responses sampled from the new, shifted policy distribution. To explain this, let's start with the original reward model. It's trained using a dataset of comparisons between two model responses generated by the same prompt. For a given prompt X, the two responses generated are denoted as Y1 and Y2. The labeler provides a preference for these two responses, where Y_C is the response more consistent with the prompt X. The training dataset of the reward model consists of these preference pairs, and the number of these pairs is denoted as n. The loss function of the original reward model can be simplified as the negative expected value of the logarithm of the difference between the reward model scores for Y_C and Y_R. Here, R_theta denotes the reward model, which is often initialized from the SFT model, and theta represents the parameters of the reward model. When we apply reinforcement learning to large language models, the environment distribution and the output distribution of the policy model are identical. This means that the environment's distribution shifts as the policy model is optimized. We find that the reward model doesn't significantly distinguish between responses sampled from the same prompt in the shifted environment. To measure the degree of difference in the responses' scores, we define a difference loss function for the reward model. Let's say we generate a sequence of responses multiple times under the same prompt using the policy model. The difference function is then the average of the absolute differences between the reward model's scores for all pairs of responses. When there's a shift in distribution, this difference function tends to have a lower value. However, a reward model that aligns with the shifted distribution exhibits a higher loss value, indicating its improved ability to distinguish between responses. To restore the reward model's ability to distinguish responses sampled from a shifted distribution, we introduce meta-learning to iteratively train the reward model to align with the new environment. Specifically, we maximize the difference loss function in a meta process and perform the meta update before the standard gradient update of the reward model. The meta process can be represented as a meta gradient ascent of the difference loss function on a mini batch of the meta dataset sampled from a shifted distribution. At each step of the training phase, the parameters of the reward model are adjusted according to the ascent direction. Next, we compute the gradient of the original loss function with respect to the updated parameters of the reward model on a mini batch of the original preference pairs dataset. Note that the Meta-RM optimization using this gradient is performed over the reward model parameters, whereas the objective is computed using the updated reward model parameters. In essence, Meta-RM aims to make the reward model learn more about the original preference pairs that provide more differentiation between responses sampled from the shifted distribution. The Meta-RM optimization is performed via gradient descent and the reward model parameters are optimized accordingly. To clearly illustrate the aim of Meta-RM, we derive the gradient for optimizing the reward model. This gradient is essentially the derivative of the original loss function with respect to the updated parameters, multiplied by the inverse of the derivative of the updated parameters with respect to the original parameters. We then apply Taylor expansion to the original loss function about the point theta, which can be written as the original loss function plus the product of the derivative of the original loss function and the difference between the updated and original parameters, plus a term that can be ignored because it's infinitesimally small. Substituting this into the equation for the gradient, we find that the Meta-RM optimization essentially adds a sum of dot products to the original loss function. The dot product computes the similarity between the gradient directions of the meta loss and the original loss with respect to theta. Specifically, when the direction of minimizing the original loss on the preference pairs and maximizing the difference between the scores of the responses are similar, the dot product of both is greater. In such cases, the gradient in the meta-RM optimization is larger, and the reward model can learn more about these preference pairs. Conversely, if the gradients are in different directions, these preference pairs may not be more helpful in aligning with the shifted distribution, so it's necessary to reduce the degree of optimization. The full algorithm is detailed in the algorithm section. Section Summary. In this section, the authors introduce meta-RM, a method that aligns the reward model with the shifted distribution in policy model training. The goal is to maintain discrimination of responses sampled from the new distribution. Meta-RM achieves this by minimizing the loss on original preference pairs while maximizing the differentiation between responses sampled from the shifted policy distribution. Meta-learning is used to iteratively train the reward model to align with the new environment, enhancing its ability to distinguish between responses. Section 3.2.1 Experiments. We conducted several experiments to evaluate our method's performance. We compared our method's responses to those of the SFT model, and the results are presented in a table. The table shows the win, tie, and lose ratios for each round of PPO training we conducted using meta-RM. To further illustrate the effectiveness of our method, we also included the best performance of our method during our loop process. For the generation dialogue and summarization tasks, these were rounds 3 and 4 respectively. We compared these results with other baselines, including the vanilla PPO. We evaluated our method using both GPT-4 and human assessments. The results showed that our method consistently outperformed the SFT model in each round. The improvement was particularly noticeable in the early rounds. However, we noticed a decrease in the win rate in the 4th round of the dialogue generation task and the 5th round of the summarization task. This suggests that there is a limit to how effective our method can be, and this limit varies depending on the task. Our method significantly outperformed all other baselines. The human assessments were closely aligned with the evaluations conducted using GPT-4. Therefore, we decided to primarily rely on the assessments from GPT-4 for our subsequent experimental analyses. We also evaluated our method in out-of-distribution (OOD) scenarios. Our method continued to outperform the baselines in these scenarios, indicating that it can be used to achieve alignment in a new domain without the need for costly preference labeling of a set of queries. This significantly reduces the training costs for ERM training. However, we did notice a slight decrease in the win rate in these scenarios, which could be due to the tasks on OOD involving a shift in query distribution compared to in distribution context. We also compared the reward score difference distribution of our method-trained reward model and the original reward model on the validation set of the metadataset. Our method generated a significantly greater reward score difference for different responses to the same prompt than the original ERM. This suggests that our method improves the reward model's ability to distinguish under a shifted distribution. We plotted 5 training curves on the hydrogen hydride RLHF dataset, 1 for the vanilla algorithm and 4 for our method in different rounds. Our method consistently showed more pronounced and stable improvements of rewards. In the 3rd round, our method achieved a significant increase in reward and a further reduction in perplexity, PPL, compared to the previous round. This suggests that our method effectively enhances the reward model's ability to distinguish, overcoming the limitations of vanilla PPO. However, in the 4th round, while the reward continued to increase, PPL showed an initial increase followed by a slight decrease. This suggests that the reward metric may not be entirely reliable in later rounds, indicating a limit to our method. The reward model is a key component of the RLHF process. It integrates human preferences and feedback into the learning process, guiding the optimization of the AI system towards objectives aligned with human preferences. However, using human feedback in RLHF presents certain challenges. Human preferences can be noisy and ambiguous, which can negatively impact the accuracy and effectiveness of the reward models. The feedback may also contain inherent biases or misalignments, influenced by the evaluator's own goals or perspectives. Another important aspect of RLHF is the generalization capability of reward models. These models are typically trained on specific datasets, which might limit their applicability across different contexts or scenarios. The models might perform well within the dataset they were trained on but struggle to maintain the same level of performance when faced with new, unseen data. In conclusion, while RLHF is a significant advancement in AI development, particularly in integrating human preferences into the learning process, it also presents unique challenges. These include the inherent noise and ambiguity in human feedback, potential biases in the data, and the generalization limits of reward models trained on specific datasets. Addressing these challenges is crucial for the advancement and ethical application of RLHF in AI systems.